All right, good morning, everybody. The homework assignment that you have related to inflation, which is what we were working on last week, that inflation assignment is due on Thursday before class. I know the last several assignments have been pushed to a Friday afternoon, but this one's going to be due on Thursday, and the reason for that is that because with the upcoming holiday, they're restricting the hours that graders can work, when time cards are due, and all that sort of thing. So it's just kind of related to the holiday schedule that's coming up. And by the way, it's not listed on the announcements, but I assume all of you have probably been keeping a pretty close eye on the fact that we're not going to be here next week. We're all going to be on vacation, right? So a week from today, a week from Thursday, we won't be here. Today we're going to be covering a completely new topic. And I'm really excited for this because so far in the semester we've been learning about decision making, where you've learned techniques to compare alternatives, but we've always just kind of taken it as a given that the amounts mentioned in the problem statement are accurate. You know, in the problem statement it would say how much something's going to cost and how much revenue it generates, and we just kind of went with those numbers without really asking whether they're realistic. Now in this new chapter, it comes from chapter 15 in the textbook, we're going to be identifying some techniques that are used to come up with accurate cost estimates. And we'll address three different methods today: unit method, cost index, and learning curve. By the way, one other announcement, I've already started grading the projects. I've just got a few more left to do. And so if you have any questions about your score or the comments that I provide, you can stop by during my office hours and I'd be happy to go over it with you. Yes? Oh, you guys need to see that? Thanks for letting me know. Well, you can watch the video if you need to see it. You just listen. All right. Thank you. So, again, Thursday, homework. Next chapter is 15. Unit method, cost index, learning curve. Wait for it. There it is. All right. Other questions or comments? All right, so we use cost estimates for all the analysis that we plan to be doing, whether it's private sector projects where we're looking for a rate of return, whether it's a public sector project and we're analyzing the cost effectiveness or the benefit cost. Cost estimates are used as the foundation for all of those previous techniques, and sometimes it can boil down to if you know you're going to do something but you're not sure which features to add or how much you can afford to spend on a certain item, then cost estimates are used for that as well. And so in terms of public safety, you maybe have seen in airports that they have these AEDs, as they're called, an automatic external defibrillator, which is if someone's having a heart attack, could shock them and bring them back to life. It's a pretty expensive piece of equipment. Another accessibility-related piece of equipment are wheelchair lifts. And so cost estimates can be used when you're designing a facility to figure out in an iterative way, going back and forth between the revenue estimates and the cost estimates, how much you can afford to spend in a certain facility and which features can be justified if you're looking to upgrade. Our textbook identifies three different rules or guidelines that should be followed when we're making cost estimates. And these are kind of developed because of mistakes people have made in the past where cost estimates were put together poorly and it caused a really big problem. So sometimes you see that in rules or guidelines that you'd think, well, why do they have that policy? It seems odd. But it's because it's come up before. And so in the past, bad cost estimates have come when the information that it was based on was a really narrow set of circumstances. So for instance, if you were using data from Anchorage, Alaska on what it costs to build and insulate a warehouse, that data, because it's in a really specific environment, may not be broadly applicable to the entire United States. The insulation and building requirements in Alaska are probably pretty specialized because it's really cold, has heavy snowfall, and that may not be applicable if you were going to try and take that cost estimation data and apply it to situation in Florida. So using reasonable data means to use data that comes from a representative sample of what's out there. and it can be considered representative of the current situation that you're planning on. Rule 2 is to use accepted theory and techniques. And some of the techniques that you've used so far would be like the least common multiple technique, early termination, contract services. You know, those are accepted methods that have been analyzed and used for a lot of years. And so if you're developing some new method for doing an analysis, that's great, but you need to see how it maybe is different from the accepted methods, have other people checking on it. And so when I was in practice, engineering practice, one of the things that a lot of people would do is they'd make their own spreadsheets to solve like structural calculations or hydraulic calculations. And spreadsheets are a really useful tool, but there are more standardized tools out there that are accepted and validated. And so when you build your own thing and other people haven't checked it, you may get mistakes out of that theory or out of that technique. So that's what rule number 2 is, basically use accepted methods when you're analyzing data and projecting costs. And the third thing about avoiding bias is just that if, for example, you're a purchasing manager for a company, your purchasing decisions should be based on what's best for the company and what's most economical, and not which salesman is the friendliest. You know, if you go with one supplier, are they going to bring in lunch to the office, that sort of thing. And so avoid bias and decisions that aren't based on the economic fundamentals. So the book has more information. This kind of a summary of the rules of cost estimation. Now I'm going to tell you about one method for cost estimation that's pretty common in construction and engineering as it relates to a project I did a few years ago with the Division of Highways. I was involved with a research project where what we were looking at is how when the water goes through underneath a bridge, it can scour the rocks that support the foundation. And so you can see that the rock that this concrete slab is resting on over time has been scoured and eroded, and that kind of threatens the viability of the bridge if the load that's supposed to be transferred to a rock, if the rock is broken and missing. So what we did in that project was we needed to collect a bunch of rock samples. And so the way that we came up with a budget estimate for how much that was going to cost to drill down through the bridge deck, drill through the concrete, and then get a sample of the rock underneath all of that, well, we had to consider what's the cost of getting the people who can do that thing on site, you know, the mobilization cost. And then you had to consider what's the cost of the equipment that's going to be needed, and are there consumables like the drill bits that are going to be burned through as they're drilling downward, and what's the cost of the people who are there on site, what's the cost of maintaining and protecting the flow of traffic. So you can see the traffic cones there, so you have to account for precautionary measures since you're closing one of the lanes of the bridge, to get people still going through, but for it to be a construction site it also needs to be safe. We looked at what is going to be the cost of having someone on site to log the samples that are taken and to wrap and preserve them, the transportation expense of getting it from the field back to the lab. So there's just a lot of different components that went into the overall cost estimate. We couldn't just, I'm always really suspicious when a contractor comes to my house, just looks at something that needs to be done, like painters. I had painters at my house in the spring, and one person was giving me a cost estimate. He just walked up, looked around a little bit. He said, "Oh, how about $5,500?" And there was no analysis there. He was just picking a number from thin air, and probably, since he didn't want to underbid, he was overbidding, you know, like increasing the estimate of the price because he was just guessing at it. But the one who I ended up selecting had a more detailed estimate, actually measured the area, the exterior area of the house, and knew how many coats of paint there would be, noticed where scaffolding was going to be required, and actually took the time to put together a detailed and thorough estimate. And that had a lot more accuracy and built more confidence in me. So we're going to talk about that kind of cost estimation today, where we look at the detailed components that are associated there. But before we do, let's revisit some of the terminology that we've discussed before when we're classifying costs And I think that we've talked in the past about the difference between direct and indirect costs, and how when you are manufacturing Twinkies, for example, if you have a factory of some sort, then the direct costs are ones that are specifically tied to the production of the thing. So if you can say how much input it requires to make a certain amount of output, chances are that that's a direct cost. And so flour is a direct cost, sugar, labor of the workers. But some expenses, you can't directly tie the question of how much is needed to make a certain amount of the thing. And so in contrast to direct costs, indirect costs are those such as computer systems, accounting services, the rent of the building, where you can't say how many accountants it takes to make the Twinkies, because it's not directly related, it's indirectly related, where all of these things are important and you need them or else you can't have the business functioning. But because we can't directly point to the input and output relationship, we have to recover them in a different way. So that's the difference between direct and indirect costs. In cost estimation, there are two competing methods for identifying how much a cost is going to be. And when I was just talking about the painters, the painter that I selected did what's called a bottom-up approach. He considered, how much equipment was going to be needed in the job, the direct materials like paint and brushes, the amount of labor from how long it was going to take for him and his laborers to do the painting. If it's related to manufacturing, you may have to also include an estimate of the costs associated with maintenance and operation of the equipment. So all of those direct costs are based on component estimates. So you know the cost per gallon and the number of gallons required. You look at the cost per hour for labor, and then you'd multiply that by the number of hours required. And so those are all the direct costs. Now the indirect costs, my painter has a cell phone and that he uses for business purposes, and so that's an expense where it's not directly related to the cost of painting my house, but he has to add some extra costs on top of all of these direct costs to recover the expenses that aren't directly related to a certain job. And so the payroll management, there's a company out there that probably manages issuing checks for his employees and manages the health care costs. Health care you consider as an indirect cost. And so all of those things added up are the total costs, but then most times you'd also add some profit on top of it that you want to make, where these are just really only your expenses of doing the thing, and then the profit on top of it would tell you what price you need to charge for a certain job. So this bottom-up approach, which is also known as required price, is used often in situations where there's not a lot of competition. Yes?
So from the total cost down, is that kind of like your break even, and then just your desired profit would be what you're making?
Yeah. If you set the required price to the total cost, then it would just be break even. That's right. There are some companies like Apple, for example, when they're making something that is a completely new product that most people haven't owned before, like a tablet computer or smartwatch. I mean, those things existed before Apple did them, but they weren't very common. And so Apple was able to kind of just look at what's it going to cost to make this thing, how much profit do we want, and we'll set the price based on our terms. The contrast to that in the top-down approach is when there's lots of suppliers and the item is kind of interchangeable. And you no longer have the luxury of setting the price based on what the costs are going to be and how much profit you want. In the top-down approach, it kind of is related to things that are considered as commodities. So a loaf of bread. There are dozens of different manufacturers for a loaf of bread, and you kind of don't have much of a emotional affiliation to any of them. And so if you want to go into the bread business, you kind of know, well, people will be willing to pay 99 cents for one of those loaves of completely air bread where there's really nothing to it, or $1.99 for bread that seems like a little more real and it's not just spun air. And so you'd start with some competitive price. So you're going to be a baker and you're going into the market where people are spending about $1.99 a loaf. So now what you do, when you know that that's the price target you have to hit, you start to figure out, working downward, how much you're going to allocate to each of those different categories. So moving back to the idea of electronics, I have a pretty generic, cheap cell phone, and it was in the, when it first was released, I bet they were targeting $199 for the price they were going to get for that. And so they thought, of the $199, probably we'll get $10 or so profit, we'll have $20 of indirect costs, and then the components, let's see, they're going to budget a certain amount for the screen, a certain amount for the RAM, they have to account for how much storage is going to be there, all the different components that go into making the thing. They're kind of moving the money around until they reach an equilibrium that they're happy with and then go into production. But that's an illustration of the top-down approach, where you're starting with the price rather than starting with what's the price of the components. You start at the top and work downward. So in your project, I asked you, I mean, I didn't call it the bottom-up approach, but what I was hoping to see is that you'd actually consider, after you graduate, what are your expenses going to be? What's going to be the cost of your rent? What's the cost of your food, your phone, utilities, all those things that, you know, for the life that you want to have, what is it going to cost you? Rather than just saying, I'm going to spend $500 a month on food and utilities combined. And that would be an example of a top-down approach, where you're not actually looking at what you want to do and what it's going to cost, but you're starting with a limit and working downward and allocating based on that. So there are two different techniques, and they're both valid in different circumstances, and sometimes you can go back and forth between the two before you finally identify what you're working towards and what you want the expenses and the allocation of the resources to be. In cost estimation, you can spend really a long time putting it together, and I noticed this in the project, that some people spend really a lot of effort getting an accurate estimate of how much they're going to be spending. Let's see, that maybe they would look at rent in all 50 states. They consider, you know, a representative city in each of the 50 states, and you can tell that that way overboard estimate would maybe be more accurate than a quicker estimate. But what this figure is showing is that your accuracy improves as you spend more time putting together the estimate, but it starts to taper off, where you're spending more and more time putting the estimate together, but the improvement in accuracy is declining. The rate of improvement is getting less and less as you spend more time on it. So in 10 minutes you maybe could put together a really basic estimate that has plus or minus 30%, but if you spent a week coming up with the estimate of material costs for a building like we're in, for instance, you could look at the cost of the carpet, the cost of the electrical receptacles, the cost of the light bulbs, and, you know, try and optimize each one of those. It's going to take more time and it'll be more accurate, but there's this, the important lesson here is that there's a diminishing returns the longer you spend on estimates. Yes?
So on the estimate accuracy,
Mm-hmm.
so we should do it, if it takes longer, we should do it for like big projects like the building itself.
Yeah, so how do you know how much time to spend? Well, if you're doing a project like the building that we're in, where it's $50 million, it may be worth a young engineer's time, you know, a month of an engineer's time to get the accurate cost estimates. You know, this building was, I think, built where the contractors all bid on it. And so, you know, contractor A wants to know how much it's going to cost to build this structure, and so they have to build an estimate. And so if they just spend 1 hour on the cost estimate, just kind of looking at, well, how many square feet is it going to be multiplied by what was the last building that we built? That would be, there's a risk that either they'll charge too much and they won't win the contract, or they'll bid too little and they will get the contract, but then they'll have to construct it at a loss. And so the consequences for a really large project would kind of give you a good motivation to be more accurate in your cost estimate. And so you're kind of balancing how important is the information with how much does it cost for you to generate the information. And probability is one way of looking at it. If spending an extra week putting together the cost estimate improves your chances of getting the job and being profitable, then you'd have to look at how much is that improvement in profitability and improvement in probability of getting the project, how much is that worth compared to the cost of generating the estimate. So there's no cut and dried like formula that tells you how long to spend on an estimate, but you're right that the more important and the more expensive the project it is, that increases our appetite for cost estimation. All right. In most of the previous semesters, I've included a question on the final exam related to this figure, so it's important. What this shows, it comes from the textbook. There are 3 different trends that are being illustrated in this figure, and they're trends that on the horizontal axis have to do with time. You can see here it says that time is moving onwards to the right. And so at the beginning of a project, what this is calling the acquisition phase is where you're beginning to do planning for a project, where you're looking at what are the needs for the item. So maybe the project is building a factory. So if you're thinking about building a factory, the first thing that you do in a project is you look at what does the factory need to do. What kind of capabilities does the equipment require. And then a conceptual design is where you're just figuring out what the layout of the equipment inside the factory would be, and it gives you a sense for how big the building needs to be. Maybe now you're starting to look at secondary things like where the electricity would be placed, how big the wires need to be, that sort of thing. The detailed design is where now you're moving on from just the basic design and you're actually planning for how strong the floors should be, how tall the ceilings are, what kind of girders and beams to be putting in. And so all of that occurs during the acquisition phase. And what you'll notice is that these trends are showing, the first one that's going up is the cumulative committed life cycle cost. And so committed means you've made decisions about doing a certain thing. You haven't actually done it yet, but for example, you've decided that you're going to build the warehouse out of steel rather than concrete. And so once you've made the decision, that kind of locks you into a path of purchases and all of the consequences that come from that path. And so the committed life cycle cost is in front of the actual cumulative life cycle cost. And this is related to where did you actually spend the money. So if you look at how steep this is, when the curve is steep, that means you're making a lot of decisions about how to spend the money. You haven't actually spent it yet, but during the acquisition and the planning phase, you're making a lot of plans and designs, and so most of the cost of the project has already been decided before the project is constructed and utilized. Now, as for when are the dollars actually being spent, this gets the steepest. The cumulative life cycle cost increases the fastest during the phase where you're producing or constructing the item and using it, so when the factory is actually in use. And then at the end, the last thing during the operation phase is the retirement disposal, so having to find some place to retire the equipment. It may be construction and demolition waste if you're tearing down the warehouse at the end of its life. So the main thing here is looking at when are you spending the money, when during the decision and planning phase. So this figure that's decreasing makes the point that early on in a project you can make decisions and changes that are going to save money in the project. And if you do it early, if you make an an improvement to the plan early on, you can save a lot of money because very little of the money has been spent yet. But halfway through the project, it's hard to save money because you've already done so much planning and you've made so many commitments about how the project is going to be that the potential for savings has declined quite a lot as time moves on. So you can see at the end of the project, when it's already been used and built and planned on, and the only thing left to do is retire the equipment and dispose of it, you have essentially very little opportunity for savings, because you may go with vendor A or vendor B to haul away the waste, but the overall life cycle cost, a very small fraction of the overall life cycle cost, has to do with the retirement and disposal. So that, again, the take-home message of this is it really, you get the most savings when you do the changes early on rather than at the end of the life cycle. One of the first methods that we're going to work through today is called the unit method, and it's just looking at the cost of a project based on how many units of a certain item is needed and the cost per unit. And so if you knew the cost per gallon of paint, the cost per paintbrush, the cost per laborer to have them on site, then you'd come up with the total cost just by adding up all of the individual components. And so some pretty typical cost estimates, for example, if you're looking at the cost of operating a car, the federal government has a reimbursement rate. I think it's maybe gone up a few cents since I put this slide together, but back when I made this slide, the federal reimbursement rate was 52 cents per mile, and that was just a commonly accepted average for the cost of operating a car. In the United States, the cost of building an interstate highway is about $6.2 million a mile. Constructing a house, we can put together the cost per square foot, concrete, and so on. These are just examples of how you would have the unit cost and then multiply it by the number of units of that thing that's going to be used for a project. So in today's in-class exercise, we're just going to do the first of these two problems related to the cost estimation with the unit method. So do part one, but we won't do part two because we have to keep moving on to another technique. All right, so in part one, it's just about a gas pipeline. So use the data that's given here to come up with what's the overall cost for the pipeline based on each of these components that we know about. When we're doing the unit method, we're just breaking down the project to as many pieces as we can think of and then estimating the cost of each one individually. And that way, if we've made a mistake in one particular category, it doesn't necessarily affect the others. And so our estimate of the cost as it relates to steel here of $137,700, well, if the price of steel went up between when we were doing the projection and when the project actually was undertaken, then we just have to estimate this one component of the cost estimate and all the others would be unaffected. So the unit method, there's an infinite number of word problems that can be created that rely on the unit method, but are there any questions about this example? Did anybody else get through to 566,700? All right. So where do you get the data that goes into a unit method estimate? For example, here where it was saying 45.90 a ton for steel, or the machinery and tool costs. Well, one of the valuable sources of data and how they change over time can be cost indices. And so let me show you an example of what a construction cost index looks like. It's a table of data that's been collected over the years, and what it shows is, according to one reference year, what prices have done, how the prices have changed over time. So you'll look here in this cost estimate, it says that year 2005 is when they set the cost estimate, the index to 100. So this is for the price of a new single-family house under construction. So in 2005, the average house cost 100, and you can think of it as a percentage, 100% of this baseline year. And then in 2006, the average price was 6% higher. And so if you wanted to know, if you had a $100,000 house in 2005, then you can find out the cost of that same house in 2006 by multiplying the price by the ratio of the index. So we'll look at a formula in a minute here, but you'll notice that for a couple of years the prices went down during and after the financial crisis that we've talked about a couple times before, but then prices rebounded significantly, and now in 2018, at the end of that year, the price estimate was at 130, where 100 was the baseline year. And so you'll know that they'll notice that they also went back in time and calculated the average price for all of these previous years as well. So the house that cost in 2005, the house that cost $100,000 back in 1964 would have only cost $12,400. So this is an index that shows the change over time. And it's not just for construction. They also have similar indices that are available for the consumer price index is, let's see, I think I have, they have it for things that are related to just the average American and where they spend their money. So this Bureau of Labor Statistics, a government agency, has the cost of living broken down into categories like food, and they're saying that 13% of the average American's budget goes towards food. Out of 100, 13 goes to food, and you'll look that they've broken it down into food you eat at home versus food you eat at restaurants. And so they have all of these categories, and they know on average what percentage of people's income gets spent on each of them, and then they track how the prices have changed from month to month. This is where those price estimators are going out and checking on the cost of certain baskets of goods all across the country. And so they have all sorts of different categories: food, beverages, utilities, transportation, clothing, entertainment, information technology, and so on and so forth. And so that's an example of another kind of price index that's available, and it's changed over time. This is a good illustration of how you can deal with the cost of inflation, is to look at how is the consumer price index adjusted over time. And so in the same way that the construction price for a single house was taken to a baseline of 100 units in 2005. It looks like this cost index has as its baseline year 1984. That's where the transition, well, maybe 1983. So if you would need $100 to go towards the cost of living in 1984, nowadays we would need about $250 to buy the same things that in 1984, 1983 would have cost 100. Oh, here it's saying the baseline is 1982 of 100. So these cost indices, there's a whole variety of them, and they have construction cost indexes for different types of construction, like chemical plants, medical facilities, and so there's all these specialized different cost indexes that you can find. And the idea is to make a ratio to use old cost data and project it into the future. Now here's the formula that shows how you'd use that ratio. If you knew that back in 1984 you had a cost of a house that was $100,000, that was the cost in that previous time, and you multiply it by the ratio of the cost index now to the cost index then, you can find what the cost of the item will cost today, how it's going to be changing over time. And so to practice that, if you turn on your in-class exercise to the second page, I guess it's the third page where we're doing this repair garage, we have a situation where we made a repair garage back in 2004, and we know how much it cost back then, and we want to find out what's the weighted cost index. And so a weighted cost index is looking at the index for each of these different components that go into it, the labor, materials, and equipment, and then you multiply it by the decimal of the weighting. And so 175 times 0.3, 145 times 0.2, and so on and so forth, and you come up with like the average weighted cost index for 2004, and then you can use that to estimate what's the cost of constructing a similar thing in the future when each of the components are costing more than they used to previously. So here in this problem, what you're going to do in step A is calculate a weighted index for each of the years that we're interested in, and then use the known cost of $650,000 to come up with an estimated cost in terms of 2008, what it would have been. So just to see if you're headed on the right track, I've got the weighted index from 2004 up on the screen there. And so we're looking at each of the different constituent components and weighting them according to what fraction of the project they account for. So the weighted cost index of 149 is what you'd use in the denominator of the ratio if you're predicting what the cost in 2008 will be. So the index for 2004 should be 149. Then the index for 2008 should be 178.5. And when we know both of those, it allows us to take the overall cost estimate from 2004 and tell us what it would cost in 2008. So just accounting for essentially the effect of inflation. And then since we know on a percentage basis how much of the project goes towards each of these different categories, then we can take the overall estimate and break it down into the smaller category estimates by multiplying by the percentage. By the way, when I've graded the exams and some of the homework assignments, sometimes it's tricky to know if you've got the right answer if you don't put the comma in. And so if you're not already in the habit of putting commas in to identify where thousands begin and where millions begin, do that. It's better to have 778, 691 rather than 778, 691.28. It just can all run together if the comma's not there. Any questions about this in-class exercise? All right, our third and final topic for today has to do with how quickly people learn things and how that affects the cost estimates. This is the picture of a garment factory, and sometimes these are colloquially known as a sweatshop. And what's kind of amazing, if you've ever seen video of somebody working in one of these places, just how quickly they can sew like a shirt or a pair of pants. It's almost astonishing, and I'm always impressed by it because the only exposure I ever had to sewing was like a home economics class in middle school where we sewed a pillow or something really simple, and I could barely sew a straight line, but then once these people have been doing it for several years, they can sew the seam of pants where they're going around a curve and have just a millimeter of extra fabric on either side, and just the skill is almost unbelievable. So let's just use an example to illustrate a technique that we're going to learn. And let's say that the first time she tried to sew a shirt, it took 12 minutes. And that is what we're going to call K. K is how much input was required the first time something was done. And what we're going to be modeling with the formula that we'll see in just a moment is how quickly somebody improved and reduced the amount of input that's required to make the thing. So if the input is time, we'd expect the second time she sewed a shirt, it's going to take less than 12 minutes to sew it. Now, automation makes things a lot easier, and automation can improve a little bit, but it may not have the same trend that we expect to see when the learning curve applies to a human. Let's just take a quick look at a factory. It's the warehouse of the future. So when we're talking about learning curve, they can look for optimizations of the automated machines as well. The first term that we identified, the K, back in the case of sewing a shirt, remember that K is how long it takes you to do it the first time. There's a new term, S, which is the having to do with the learning curve and how long it takes you to double your productivity. So when you're going from, for example, the 5th time you did something to the 10th time that you did something. So how much input was required once you've got twice as much experience as you had before. That's what we're going to use for our S factor in the formula. Now, over time, the general trend is that it's going to use less time to do something the more experience you get, but the improvements are going to slow down. This is model of the learning curve is sometimes also called an experience curve or the manufacturing progress function. So K we've already talked about. That's how much was required the first time you did it. The S curve, the learning curve slope parameter, is the ratio of time to double your experience. And then to find out how much time it's required to do something, the youth time. So for example, if it was sewing pants, how long will it take you to sew the 10th pair of pants? You'd put in the amount of time that was required the first time you sewed a pair of pants, and then here you would use the N that is based on the learning curve slope parameter. And I think probably this will make the most sense if we take a look at a quick illustration here. Let's say that the first time that you sewed a pair of pants, it took 85 minutes, and so that is K. And the second pair of pants takes 76.5 minutes. So that doubles your experience when you're going from having completed one pair to completing 2 pairs of pants. You've now doubled your experience. And so from that, we can calculate the factor S. So S is 76.5 minutes over 85 minutes. And so the learning curve slope of 0.90 applies here. And we could check to see if that's true because it also tells us how much time was required for the fourth pair of pans. And so if you're going from having completed 2 of them to completing 4, that's also a doubling of the productivity. So another way of looking at it would be the 68.85 minutes relative to 76.5. So again, that works out to 0.90. So it seems like the learning curve slope is consistent over time. So if we want to find out how long it will take to sew the 10th pair of pants, what we have to know is what is n for this learning relationship. And so it's going to be the log of 0.9 divided by the log of 2 to get the n factor. Okay, so that is negative 0.045757 and so on and so forth, divided by 0.30103 and so on and so forth. So n is negative 0.1520. So when we have the n, that's the exponent in the learning curve function. And if we want to know for the 10th pair of pants, then that means u is 10. Because we want to know how much input, which is time, is required once you get to the 10th pair of pants. And so z sub 10 will be 85 minutes, which remember is the input required the first time, to the power of, times 10 to the power of negative 0.1520. Okay, so that means it would take 59.9 minutes when you're sewing the 10th pair of pants, because you've got more experience, you're working more efficiently, you've learned maybe some tricks along the way, and it takes less time to do it. Yeah.
So, but didn't it reach a point after, like, say, like the 20th or 30th, that the finish of the linear curve will eventually become just a straight line?
Mm-hmm. Yeah. Once you've learned all the tricks and there aren't really any more optimizations or improvements you can make, there's just a physical limit to how quickly the hand can move over the sewing machine, and maybe a limit to how quickly the sewing machine itself can have the needle coming up and down through the threads. Through the fabric. So you're right. It will reach a plateau. And so if we wanted to look at what that trend looks like, we could put it together in Excel pretty easily. We could make a quick spreadsheet where we have our S factor that we've already S up on the board. We decided that was 0.9, and N is negative 0.152. So now here, if we just have the equation that we're going to put in, all right, this is our function, and we're going to have the pair of pants and then the time that's required to do it. Okay, so the first pair, the second pair, third pair, and so on and so forth. And let's just go through like the 20th pair. And what we'll see is that very trend that you were just mentioning, is that you don't get that much faster. I mean, when you're going from your first time to your second time, you get a lot better at it. But then those improvements slow down. All right, so it is going to be the first one. I'm anchoring that reference times U, which is whichever row we're on, because that's, the second pair of pants, the third pair of pants, and so on. So that to the power of n. All right, I better anchor the reference to n. So let's see, it said 76.5 minutes for the second one, and that is consistent with what the previous data that we had said. Let's see, where was that? Yeah, 76.5, and so we can drag the formula down and you're making a big jump in productivity from the first to the second, but then from the 19th to the 20th, there's hardly any change at all, just a little bit better. And eventually that would go to a completely flat line. All right, so that's the idea behind learning curve. And so why do you need to know this for cost estimation? It's because when you are getting people onto a job and you're trying to estimate their productivity, you have to keep in mind that as the job goes on, they'll get better at their respective tasks and may be able to complete work more quickly than they were the first time on the job site. So let's take a look at this example of what if you were trying to solve a Rubik's Cube. This is on the back page of the handout. Now the trick on this one, though, is that K is how much time was required the first time you did the thing. And we didn't time it the first time we went. But we can back calculate K based on S. We can define the relationship of S by looking at from the second to the fourth, or from the fourth to the eighth, because both of those are doublings in productivity, or doublings in experience, that is. And then you could use that same trend and go backwards through time. So you can estimate how much time was required the first time you went, and then find out for the 100th time, what would you estimate the amount of minutes required to solve the Rubik's Cube will be.
You can set up an equation like this. So try number 4 over try number 2 is that. So since that's your S, you can put it in there. The whole thing is a function of U. So try 100, which is your U value is 100. N value.
Okay, so it looks like the first time around it probably took us 26.38 minutes. So we can kind of back calculate that based on this trend of every time we've doubled our experience, the amount of time it takes is only 91% as long. So it only took 91% of the time 2 amount to do time 4, and 91% of the time to go from time 4 to time 8. So then what we can say is that 24 must be 91% of the original amount. So that's where 26.38 minutes comes from. And once we know that, we can just substitute it into the overall learning curve formula and say that for the 100th time you do the Rubik's Cube, then it should only take you 14.09 minutes. So just to recap, today we talked about the unit method, which is the idea of you're breaking a project down into its components and trying to predict the cost of each one of those individually. And then we talked about 2 different modifiers. One modifier that looks at how costs change over time, and the tool that we have to account for that change in time is the cost index. And then the other adjustment to the unit method is that people get more experienced and more efficient over time, people and processes and machines, and so we can try and adjust our estimates to account for the learning curve by using this learning curve method. When we get together on Thursday, we'll dive into some additional ways of improving estimates when we're doing cost estimates, how we improve the accuracy of that. So just to revisit, the homework assignment having to do with inflation, which is last week's lecture topic, that assignment is due on Thursday before class. So if you have any questions as you're working on it, feel free to stop by, and I will see you on Thursday morning.